Cauchy's formula. So by the principle of mathematical induction, very first we are going to prove for n equals to 1. So if you are going to take n equals to 1, you will get here y dash x equals to f of x. You are going to integrate this. You will get some answer and you are going to solve this for n equals to 1 and you will get the answer. So you will easily derive this. Okay, for n equals to 1, you can use the condition y of c equals to 0. You have to take the integration and you will derive this. Now, by the principle of mathematical induction, we will assume the result is true for n and we are going to prove for n plus 1. Here, y n plus 1th derivative of y, we will separate in this way. First derivative of y, then its nth derivative. So y dash we are taking as u of x. So now you have this nth order differential equation. As we proved by principle of mathematical induction, this is true for n and we will use this to prove for n plus 1. So we have this and ux is nothing but y dash x. So by using the change of the order of the integration and using the initial conditions, you can easily obtain the Cauchy's formula and you will get this because fx is the nth derivative of yx and you can write on yx as the nth integration of fx. So you are deriving this. So what the Riemann-Liouville had done, they had taken this n is a natural number as the real number mu, positive real number mu. Okay, and they have applied that instead of this factorial function, because you are using the real numbers, you have to use the gamma function. So they have used the gamma function to derive the definitions, and the function is the LAB function. You know the definition, integration over a to b mode of fx dx is less than infinity. Okay, so Riemann-Liouville's left-sided Riemann-Liouville fractional integral operator is given by this formula where x is greater than a, and right-sided is given by this formula. So if you are taking x greater than 0, so instead of a, you have to take 0. You have to remember these formulas when you are going to derive any solution of any fractional differential equation. Okay, so these are the Riemann-Liouville's integral operators. And we will see here the some basic example. If instead of f of x, we are going to take x raised to nu. So what will be the answer? So we had to put instead of f of x, we have x raised to nu. So f of t will be t raised to nu. And now we are going to take x common. So x raised to mu minus 1 will be common. We will get this. And here t by x, we had to assume u. So you will get x du equals to dt, and as you are taking t equals to 0, u is 0. When you are going to take t equals to x, u is 1. So you will reach to this integration. Okay, after the simplification, you will reach here. Now, if you are able to identify, then you can easily identify this is nothing but the beta function. So we will see the definition of the beta function. Beta function is given by integration 0 to 1 z raised to a minus 1 minus z raised to b minus 1 dz with these conditions. And the relation between gamma and beta function is gamma a into gamma b upon gamma a plus b is nothing but beta of ab. So we are going to use this definition and this relation. So now see, we need z raised to a minus 1. So we have to take nu plus 1 minus 1 and this is mu. So we will get beta nu plus 1 comma mu. And by using the relation of the gamma function, we can reach here. So ultimately, muth order fractional derivative of x raised to nu is this. Okay. In some books, instead of I raised to mu, they are using d raised to minus mu as derivative and integration. Both are reciprocal of each other. Here we have to take nu is greater than minus 1 because gamma function is not defined on zeros and negative numbers. Okay, so that's why the condition will be nu greater than minus 1. Okay, so now the definition of Riemann-Liouville fractional derivative. So this is the definition of the fractional derivative. You can see here in the definition of the derivative, you have to use the integration. So ultimately, if you are to learn the fractional calculus, you should know the calculus, differential calculus and integral calculus both. Then you can go for this. Okay. So this is the definition of the fractional calculus derivative, fractional order derivative Now we will see same way the example for x raised to nu. So by you have to take u equals to n minus nu, where u is lies between 0 and 1. Here we are going to take n equals to 1. So you have u equals to 1 minus mu. So if you are going to take instead of u 1 minus mu, and you know the integral operator, if you are going to apply on x raised to nu, your answer will be, you have now instead of mu you have 1 minus mu, so we are going to change mu to 1 minus mu. So after the simplification you will get this. So ultimately the muth order fractional derivative of x raised to mu is this. Okay, it is easy to derive by using the muth order integral derivative of x raised to nu. You are knowing integral operator, so you have to apply that here, but instead of mu you have 1 minus mu, and d raised to nu will give you this. Okay, so this is the final answer. Okay, these are the few examples. You can get the integral operator and differential operator of order mu of this sum functions. As you know, for x raised to nu is this, and from that we will take the specific values of nu and mu. You will get this. For the constant, x raised to 0 is constant. So you can see here derivative is not 0 for the constant functions. Okay, these are the more. So these are some more. Now, if you see this definition, the question can be arise in our mind. At that time also arise what that will happen if you are going to take instead of the derivative first and integration afterwards. अगर हमने ये order change कर दिया, then what will happen? Whether that will work or not, we will get the answers. Will it call the fractional calculus differential operator? It is acceptable. So yeah, that definition is given by Caputo. So Caputo defined this with the fractional differential operator. He has taken first the derivative, then the integration. Okay, now we will see the one example only for the difference between the Caputo fractional derivative and Riemann-Liouville. So if you are going to take f of t equals to 1 constant function, then the Caputo derivative is 0, but Riemann-Liouville derivative is not equals to 0. Similarly, for f of t equals to t, you will get the same answer, f of t equals to t square. It is not necessary for all the functions you will get the same answer. If you are going for the e raised to at and e raised to minus at, so e raised to minus at will give you the same answer for both, but e raised to at will give you the different answers. Sin t, cos t, sin t will give you the same answer for both the function, but cos t will give you the different answer. So this way you can easily verify by using the definition of the functions for the fractional integral operator and differential operator and the definitions of the functions. It is easy to obtain. Yeah, but you have to use the sub concepts of the different functions. So that's why I have not taken these examples, but you can see that. Okay, these are the rules. Linearity rule is followed by the differential operator, but they are not satisfying successive differentiation, Leibniz rule and chain rule. These are not satisfied by the fractional differential operators. These are the generalized fractional integral operators which are given by Edley-Coburn. He has given the generalized fractional integral operator with this given condition. Then the differential operator is generalized by the Hilfer. We are not going to see much on this because you need a different kind of the equations to solve this of the different types. Then these are used because at some point they will stuck, so they have generalized the definitions and they are getting these kind of the definition generalized for the order mu and type nu with this condition. This is given by Hilfer. So this is the brief for the fractional calculus, how it arises and how it is defined, the operator. Now we will move to the fractional differential equation. So as we know, if we are going for the differential equation or integral equation, means they are containing the differential operators and integral operators. So if you move for the fractional differential equations, obviously these are containing the fractional operators. So before going for the fractional operators, we will see what is the generalized function, Mittag-Leffler function, and it how it is given. So in 1903, Mittag-Leffler introduced the function which is denoted by E alpha z, and it is defined as summation n equals to 0 to infinity z raised to n upon gamma alpha n plus 1. If you observe with this condition, if you observe that this function is nothing but the generalization of the exponential function. How? If you are going to take alpha equals to 1, if this is 1, then you will get gamma n plus 1, and gamma n plus 1 is nothing but the n factorial. So ultimately you are getting summation z raised to n upon n factorial, which is nothing but the exponential function. Okay, so actually its applications are not observed before 2 decades, and after the 2 decades, it was in last 2 decades. You can see this is observed in the many problems of the physics, chemistry, biology, engineering, applied sciences as the solution of the fractional integral or differential equation. So if you are going to solve any fractional integral or differential equation, you can observe that the solution is either the Mittag-Leffler function, there are possibility, or its generalization. There are the many generalization which are given by the many mathematicians. Mostly if you are going to solve the simple equations, you will get the Mittag-Leffler function, or it's another generalization which is Wiman's function, which is nothing but the generalization of Mittag-Leffler function given in 1905. So this is a generalization. If you are going to take beta equals to 1, this becomes the Mittag-Leffler function. If you are going to take alpha beta both 1, then you will get the exponential function. So we will mostly see the examples which are containing the Mittag-Leffler function or the Wiman function. Okay. Now we will see how the Mittag-Leffler function arise in the fractional calculus equation, differential equation. If you are going to solve, how you are getting the Mittag-Leffler function. So we are taking one simple example. In the reaction diffusion process, if n of t is the number of density at a time t, and if the production rate is proportional to the original number, then d by dt n t equals to lambda n t, where lambda is greater than 0. Here lambda is the rate of production, and we are assuming the consumption or destruction rate is also proportional to the original number. So ultimately you will get d by dt n of t equals to minus mu n of t, where mu greater than 0, mu is the rate of the destruction. So the residual part will be difference of both. So ultimately we are taking c equals to mu minus lambda, we are getting this equation, and c is independent of t. So this will be the solution. You are knowing how to solve by using the method of separable of variables. It is easy to observe, or you can use a linear equation, whatever you want. Easy to solve this and you will get the solution. So now if instead of this derivative, if you are going to take the fractional derivative, suppose of order nu, then when you are going to solve this equation, fractional differential equation, you will get this as the solution, and here 1 upon gamma nu k plus 1 into ct raised to nu k. So this will ultimately give you the Mittag-Leffler function. It is easy to solve. We will see the examples and you will be obviously able to solve this equation also. There is nothing big to solve this. Okay, so you will get this as a solution. So in this way, if you are going to take the differential operators or integral operators as a fractional, so there are the chances of arise of the solution in terms of the Mittag-Leffler functions. Okay. Next, if you want to going to solve the fractional differential equations or integral equation, you should know the Laplace transform. It's basic concept, because you have to apply the Laplace transform, then the inverse Laplace transform to solve the equation. This is a one way which I am going to follow. So you know the definition of the Laplace transform. Laplace of yt is given by this formula, and yt is nothing but the inverse Laplace transform of y of s. Okay, so this is the definition you all are knowing. Then its properties, linear operator, Laplace transform is linear operator if you are knowing the Laplace transform of f of t and g of t. Okay, then the Laplace transform of the sum functions, Laplace transform of t raised to mu is given by this, and Laplace transform of e raised to at, that you all are knowing is this. Then the most useful convolution theorem for the Laplace transform. So this f of s is nothing but Laplace transform of f of t, and g of s is nothing but the Laplace transform of g of t. So ultimately integration 0 to t f of u g of t minus u du is nothing but equals to Laplace transform of f of t and Laplace transform of g of t. Okay, so now we are going to use that to find the Laplace transform of fractional integral. So fractional integral of order mu is this. Now you observe this. If you are going to see this, so this is nothing but the convolution integral. So by the Laplace transform, if you are going to apply the Laplace on this, so you are going to apply Laplace on this, and this is nothing but Laplace of this function and this function. So this function is t raised to mu minus 1, and this is y of t. So ultimately you will reach to this because you know the Laplace transform of t raised to mu. We did that. And we are assuming the Laplace transform of y of t is y of s, capital Y of s. Okay. So this way you can find the Laplace transform of the integral operator. And by using the above function, if instead of yt function, I'm going to take e raised to at, or I'm going to take t raised to nu something, any function. So you had to write down the Laplace transform of that function instead of y of s. Okay. So these are the examples. If I'm going to take the Laplace transform of t raised to nu with the integral operator for e raised to at will be this. Okay. So now the next Laplace transform of the fractional derivative. We are knowing that the Laplace transform of the nth derivative is given by this way. So this is for the natural number n. Now by the definition of the fractional derivative, we are going to write on this, and u is nothing but we are writing n minus mu. So instead of u, we are going to write down n minus mu by the definition of the fractional derivative, and this is d raised to n. This is nth derivative. Okay, so you know the Laplace transform of y and t. So if you are going to find out the Laplace transform of this, you had to find out Laplace transform of this. And you know Laplace transform of what is the Laplace transform of y and t, means nth derivative of y at t. So the formula of that you have to use here, and your yt function will be this function. This is your y of t, the whole. Okay, so the same formula you are going to apply here. You will get this answer yt at t equals to 0. So if you are going to take t equals to 0, you will get this. So ultimately, Laplace transform of the fractional differential operator will be this. So this formula you should know when you are going to apply the Laplace transform on the differential operators. Now the next, if here see here the condition of for mu is by the definition of the fractional or integral operator n minus 1 mu less than n. So if you are going to take n equals to 1, so the mu will be in between 0 and 1. So if you have given any differential equation and mu is between 0 and 1, so you have to use this form. And n equals to 2. Means if mu is between 1 and 2, you have to use this formula. So these are the formulas which we are deriving from this. If you are going to take n equals to 3, you will get the next one when the mu lies between 2 and 3. So this way you can derive from the general formula. Okay. Now the Laplace transform of the Caputo derivative. If you are going to apply the Laplace transform on the Caputo differential fractional differential operator, you will get this. These are the conditions where n is the natural number. So before solving any fractional differential equation, we will see some lemmas. So first lemma is inverse Laplace transform of this is this. So how you are going to prove this? You have to take s raised to alpha common. So you will get 1 upon 1 plus x raised to n plus 1 form. And you know the series expansion of this function. Yeah, we have the series expansion. So we are going to use the series expansion of that function, and we will apply the inverse Laplace transform on that, and we will get the solution like this way. This is a series expansion of 1 upon 1 plus x raised to n plus 1. And if you are going to apply the inverse Laplace transform on this, you will easily obtain the solution. Okay. Next result is this, L inverse of this. Here also you have to take s raised to gamma upon s raised to alpha plus as raised to beta common, and you have to use the previous lemma and inverse Laplace transform. So you will get this way. This is 1 upon 1 plus x. The series expansion of 1 upon 1 plus x is summation minus 1 raised to n x raised to n. So that we have to use, and you have to use the result previous lemma inverse Laplace transform. You will easily obtain this. Next, you have to remember, apart from the Metag-Liffer function, you should know what is the hypergeometric function, because if you are going to solve some fractional differential equation or integral equations, you will get the terms in form of the hypergeometric function. So hypergeometric function is symbolized in this way also. In some books, they are symbolizing in this way. P, F, Q, the first row, this is indicating the numerator terms. So they are writing in this way, numerator A1, A2 and so on, AN. After that, they are taking the semicolon. So you have to be careful while you are reading something at some place. So this semicolon is indicating that you are going to write down for the numerator. So then you have to, this is suppose P. Then you are going to write down the numerator B1, B2 and BQ. So on BQ. So this is your denominator terms. And then comma, whatever is your variable. So Z. Okay, so this way also you can write down. So ultimately it's showing that summation n equals to 0 to infinity a1 sub n, a2 sub n up to so on, ap sub n upon b1 sub n, b2 sub n up to so on, bq sub n, z raised to n upon n factorial. If you are taking the summation index n, so you have to use the symbol n. And here AIs, A1 sub n and all this are the Pochhammer symbols. You are knowing this. This is a condition for this series to be convergent. Okay. So if you are going to refer, so you have to be careful whether this function is defined or not, or you have to add the dummy variables 1 sub n and factorial, you have to divide and multiply like that. But we are not going more on this. Yeah, if you are going to refer, you have to remember these convergent conditions. Now we will see the some inverse Laplace transform of the functions. If these are the Laplace transform, then inverse is this. You can see here you are getting the exponential function. Here it is a Riemann function. It is a Metag-Liffer function, and then the next Metag-Liffer function in terms of Riemann's. This is a hypergeometric function. So this, see, in comma semicolon, this is written. So this is saying that summation n equals to 0 to infinity alpha sub n upon beta sub n into a t raised to n upon n factorial. Here you have the exponential function. So whatever these are the operators, inverse transforms, these are going to be used in the coming differential equation, fractional equations. And this is the Fourier transform of the uxt. You are knowing that. And this is the inverse Fourier transform. So now we will see the examples. Few examples we will see as per the time constraints. Whatever is possible, we will follow. And others you can try. I will show you the questions and you can try to become the super intelligent. Yeah. So see. This is our fractional differential equation where a is our constant. Now very first you have to observe the order. So this order lies between 0 and 1. Okay. So this lies between 0 and 1, 2 by 3. So now you have to use the formula for n equals to 1. We have written the formula. So you have to use that formula. You have to apply Laplace transform on both the sides. So this is Laplace and a Laplace of yt, because Laplace transform is a linear operator. So you can take a constant outside, and we are assuming Laplace transform of yt is y of s, capital Ys. And here the Laplace transform. So you know the formula for mu t, and if you are taking mu between 0 and 1, you have to use this formula. And this is the solution you are getting. But what is the value of this? So we are assuming this value at t equals to 0 is exist, and we are calling this as C1. This is some constant value because you are differentiating and putting t equals to 0. So you will get some constant. So we are assuming this is C1. Now we have to find out the value of C1. So ultimately we have this. We are going to take Ys common to one side, and after simplification you will get this. And then applying the inverse Laplace transform and using the results from the table, suitable result from the table, you will get this as the solution. We have the formulas for the Laplace transform of 1 upon s raised to alpha minus a, that is e alpha alpha a t raised to alpha. That is our formula. So that formula we are going to use, and we will get the answers. So ultimately yt is this. Okay, now we have to find the value of C1. C1 कैसे find करोगे? You have this. You have to apply L inverse of minus 1 by 3, and y of s is C1 upon 2 by s raised to 2 by 3 minus a. and after using that, comparing at t equals to 0, you will get this value. So C1 you will get from here. Okay, so similarly you can solve this equation. Here the mu lies between 1 and 2. You had to use this formula. You had to assume two constants here, 1 and 2. Suppose C1 and C2. So as you are solving the differential equation, same way you have to solve. You are going to apply the inverse Laplace transform. You will get these answers. And if you have given the some conditions, you can find out these unknowns. If the conditions are not given, you are not able to find out the unknowns. This is the next condition. Here you have given at t equals to 0 the value is c. So the ultimately if you are going to solve this equation, the answer will be this, because the unknown is your c. So this way you can solve the fractional differential equations. This is a one more. Here the general order nu. So suppose it is between n minus 1 to n, because you are not knowing what is the value of nu. So we are in general assuming. So by using the Laplace transform, we are getting this, and we are going to solve this. We are assuming at the 0 the derivative ck for k equals to 1, 2, 3 like that, the c0, c1, c2, c2. And after simplifying you are getting this, and you have to apply the inverse Laplace transform on this. यहाँ पे सीरीज के लिए आपके पास लेमास हैं, you have to use those lemmas and you will get the answers. Okay, similarly you can solve this differential equation also. Here we are assuming that q and small q and capital Q both lying between 0 and 1. So it is up to us. If you are taking between 0 and 1, we will get in this way answer. If you are taking 1 to 2, we had to add more terms here and we'll get the answers, because here we have given the differential operator at t equals to 0 of order q minus 1 and q minus 1 is c. We are not given for another, तो हमें यही सपोज करना पड़ेगा. We had to suppose between 0 and 1, then and only you will get these constants only, unknowns. Otherwise there will be more two unknowns. If you are going to apply that, so that answer will remain in the unknowns only. But here you have the value of this is c, so addition of this and this is c. So ultimately you have to first apply Laplace transform. You know the Laplace transform of the fractional differential operator, and that you have to take for n equals to 1, and then you have to apply the inverse Laplace transform. So after applying the inverse Laplace transform, you will get here. Here you have to use the convolution theorem, and by using that you will get the answer in this form. Inverse Laplace transform of gt, this is, and inverse Laplace transform of this function is in this form, which you are going to find out by using the convolution. Okay, so ultimately gt becomes this. और ये जो gt आपको मिला वो आपको यहाँ पे रखना है, क्योंकि इसका आंसर क्या आएगा, लैप्लास ऑफ gt, एंड इसका आएगा लैप्लास ऑफ hs. यहाँ से वही, तो gt आपने क्या लिया है ये, तो अल्टीमेटली यू आर गेटिंग दिस आंसर इन टर्म्स ऑफ द कन्वोल्यूशन. ये आपने सेट किया यहाँ पे. यू हैव वन दिस लैप्लास and one is this. You have Laplace of gs and hs, gt and ht means you have gs and hs. दो फंक्शंस हैं, तो दो फंक्शंस की वजह से आपने ये लिखा, बट यू शुड नो व्हाट इज gt. तो इसका इनवर्स लैप्लास, यू हैव टू फाइंड आउट द इनवर्स लैप्लास ट्रांसफॉर्म ऑफ दिस. So when you are going to find out the inverse Laplace transform of this function, whatever you are taking gs, you will get this function. So this is your gt ultimately, and hs will be ht. It's the inverse Laplace transform, we are taking ht. So this way you can find out the solution. Okay, now this is a sequential, means you have given more than one differential operator in one series. Suppose we are taking fractional differential operator of sigma k, and sigma k is sum of alpha k minus 1 up to so on alpha 1, where k is 1 to n minus 1 you can take. So this summation sigma k summation j equals to 1 to k alpha j, means alpha 1, alpha 2, alpha 3 up to so on alpha k minus 1 and alpha k. So now if you are going to find out the Laplace transform of this sigma k, so this will be the Laplace transform. Okay, I have taken here m because you are generally knowing the formula for summation k equals to 0. So I'm not going to change the variable in that parameter, in that index, summation index, I changed here sigma m हमने लिया है and sigma m is this, and after applying the Laplace transform as you are doing, you will get this as the answer. So if you are going to solve some question like that, you have given two operators sequentially. So how you are going to solve? You have to use the above formula. This formula you have to use, and you have to solve this example. You can easily solve. You have to apply the Laplace transform. All the conditions are given to you that you have to use. यहाँ पे आपका alpha 1, alpha 2, you have to assume that is alpha beta is alpha 1, alpha 2. So your sigma 1 is alpha, sigma 2 is alpha plus beta, because you are going to take the in sequence. So ultimately you have to solve this equation, and these are the conditions. Okay, so these are the conditions which you have to use. So after using these conditions, we can easily solve. So if you are going to solve this, you are applying the Laplace transform. So you are getting this, and यहाँ पे आपको लेमास डेफिनेशंस जो आगे हमने यूज की वो सब यूज होंगी. You will get this form, and then you have to apply the inverse Laplace transform. You will get the answer. Answer will be in the convolution, obviously, because you have two functions in each. दो Laplace transform आपको हर एक टर्म में मिल रही है. So that's why you will get in terms of the integral convolution theorem. You have to apply and you will get the solution. Now the next, if you have the double derivative, now यहाँ पे तो easy है, because this is natural number, you know formula for this is this, and you have to apply the Laplace transform on this, then apply the Laplace transform on this, and Laplace transform on constant. So constant will remain outside, and Laplace transform of 1 is 1 by s. Here you have given alpha lies between 1 and 2. यहाँ this is an important condition. If you are given alpha between 1, 0 and 1, so according to that you have to take the formula. Here it is given 1 and 2, so according to that you have to take the formula, and here you have given the values of y0 and y-0. So you are going to put all the values of y0, y-0 wherever they are appearing, and after that simplify. You take ys to one side, other terms to another side, and you have to use the lemmas whatever are given to you. Mostly these two lemmas and the formulas whatever I have mentioned, all the formulas you have to use, and you will get this solution. So you have to apply the inverse Laplace transform on this by using the lemma and definitions, and you will get this answer. See, this is from the lemma. So this is the solution. So this way you can solve. You can solve the system of two equations also. As you are solving, you have to solve this and this, you will get the solutions. And then the next, partial differential equation. Same way here, partial fractional calculus equation. So here it is partial order. So you know how to solve this. You have to apply the Laplace transform. These are the conditions you are given. X tends to plus minus infinity, uxt is 0, and u of x0 is f of x. So these conditions you have to use. You have to apply the Laplace transform. So here Laplace transform will give you this formula, because alpha lies between 0 and 1. You have given the value of u of x0, that is f of x, and Laplace transform of uxt, you are assuming uxs. And now here, see, here you have to apply Laplace transform. Now you are knowing that the Laplace transform is depending on t. So x is remain as it is. So uxt, its Laplace transform becomes uxx. Same जो यहाँ पे है, because there are the two types of the function. Suppose यहाँ पे partial derivative t की होती, then that will be changed. So you have to be careful, because it is partial derivative is x, तो आप Laplace transform को inside ले सकते हैं. After that, partial differential operator. Otherwise you can't take if there here you have t. So in examples you have to be careful. So after using the given conditions and you are applying the Fourier transform, here you will get this answer, where you have the Fourier transforms and then apply the inverse Fourier transforms, where uxs is a Laplace transform of uxt and urs is the Fourier transform of uxs, because Fourier transform you have to apply on x, and f of r is the Fourier transform of small fx. So ultimately after applying this, now you have to apply the inverse Laplace transform and you will get the solutions. And this is the Laplace transform of the continuous functions. So this is a formula. We are not going much on this. I will just show you in. So these are the formulas you can use, lemmas. Yes, formulas as you are doing for the single function, you had multiple continuous Laplace transform. So you have to use these are the examples. You can see as I shown you one example. Same way another examples. Initial conditions are changed. So according to that, you have to apply. You have to apply the Laplace transform, and that kind of examples you have to use the Fourier transform. Multiply, you will get the solutions. So here directly by using the continuous Laplace transform definition, you can easily obtain this solution. It is easy. Now the applications of the fractional calculus. If you observe, the fractional calculus was introduced in 1695, but not much work is observed from last 4 decades, and the application mainly on the modeling of systems and fractional order control. So this is in brief view of the application. It is on the viscoelastic material, polymeric material, and then fluid flow, dynamical process, dynamics of earthquakes, optics, geology, biosciences. There are the many more applications. You can see these are in the some brief, but I'm not going for this much. I just want to show you these are in brief for all. I want to show you one for the numerical methods. If you are using the numerical methods, you are using the MATLAB, then you have to use this gdiffer integral, and script file you have to use dfunc.m. I'm not using, but these people are using this for obtaining the fractional integral operator. For non-integer values orders, you can find out the integral or derivatives directly in MATLAB by using these packages. Okay, so these are the applications. This is the acceptance by the research community for the fractional calculus. There are more than 50 books and dedicated international journals, and first international conference of fractional calculus and its application was arranged in 1974 in US, when it is introduced in 1695, and a special international conference conducted by IFAC, which is conducting every 2 years in 2004 on the fractional differentiation and its application. There are more than 10,000 papers only on the single topic of modeling of complex system by differential calculus, fractional differential calculus. Okay, and till now you observe the most of the mathematician whatever I told are the international, but it is not like that. There are the many Indian researchers who are working, who had worked great works on, published a great work on the fractional calculus. Few of them are at Professor H.M. Srivastava, Professor Loknath Devnath, Professor Lakshmi Kantham, Professor Gangal Saxena, Professor Mathai. You can observe the nice work for the Professor H.M. Srivastava, Loknath Devnath, and Mathai sir. There are the books they have published on these works, and Professor Arun Kumar, then Professor Shantanu, Professor Anindya SN, Professor SN, Professor Arijit, and Professor Varsha Geji ma'am. There is a good book of her also. You can see the introduction of the fractional calculus, and these are the references which I told you. This is a fractional calculus book introduction you can find here. This is for the generalization, and this is the book for the generalization of the fractional calculus and Mittag-Leffler function. So if you are going to generalize the fractional operator, you can go for this. And this is the work by the Srivastava sir and Kilbas. This is the initial work of the Mittag-Leffler. This book is by the Mathai sir. You can find out here the fractional calculus, H function, and Mittag-Leffler function. And this book, if you want to learn for the fractional calculus, so you have to go for this book. And this is another work. And after that, one more book I want to say, if you want to see the functions, gamma function, beta function, what kind of functions are occurring in that, so you have to refer the Renwell's book for special functions. And this is a S.G. Samko's A.A. Kilbas book for the fractional derivatives, integrals, and its applications. Okay, these are the more books. This is the paper of the Viman's generalization. So this is the work which I want to present for you for the fractional calculus. So now you all have to get fractionalized wherever you find the differential equation. if you are going to learn something on the differential equation, differential integral, always try to find out what will be if the order is mu. Okay, fractional order हो तो आप क्या कर सकते. It is not necessary always you will get the answer, but you can try the answers. You can might be create the some new functions, some new definitions. There are the many definitions which are satisfying the those properties also, like chain rule and Leibniz rule and all, but not used much till now. So I just taken that so you not be more confused. Usually people are using for that. So thank you so much. Thanks.
Any questions from the participant side? Thank you, ma'am. Any participant side, any questions? Okay. No questions as of now. Thank you so much, ma'am, for an informative and knowledgeable session. And I would like to thank each one of you who is part of this webinar. Thank you. Have a good day.
Thank you, Bharti ma'am.
Thank you, ma'am. Thank you. Thanks to all of you for listening me. Okay, thank you. Bye. Can I leave now, no?
Yes, ma'am, you can.
Okay, thank you. Bye. You all stay safe. Bye.
You too, ma'am.